In this video, we're going to cover section 4.2 on antiderivatives interpreted as areas. So the objective of this section is to find the area under a graph and use it to solve real-world problems and to use rectangles to approximate the area under a graph. All right, so our first example, a vehicle travels at 50 miles an hour for 2 hours. How far has the vehicle traveled? All right, so we don't really need calculus to figure this out. 50 miles an hour, this is distance equals rate times time. The rate is 50 miles an hour, the time is 2 hours, so the answer is 100 miles. All right, however, if we treat the vehicle's velocity as a function, meaning it's 50 miles an hour would be your velocity function, v of x equals 50, and we graph this function, sketch a vertical line at the time value 2, so at x equals 2, to obtain a rectangle. This rectangle measures 2 units horizontally and 50 units vertically, and its area is the distance that your vehicle has traveled. So this would be your picture of that graph. So if you have a velocity function given, and over here you're blocked off with a ending value, in this case our time of 2 hours, the area under the curve, right? So our rectangle formula here would be 2 by 50. 2 times 50 is the area, which is 100. So that area of that enclosed space between your velocity function and your x-axis, right, is the same as distance traveled. So we're going to utilize that idea to help us solve problems in this section. All right, next example. The velocity of a moving object is given by the function v of x equals 3x, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which would represent the distance the object has traveled. All right, so we want to find the distance traveled during the first 3 hours. So in other words, for the x values between 0 and 3. And then between the third and the 5th hour, so for the x values between 3 and 5. So our velocity function that we're given is 3x. So we're going to graph the velocity function. Show it over here. That is shown on the right. So our graph of v of x equals 3x is this line. We see the region corresponding to the time interval 0 to 3 as this triangle. So for time value or x value between 0 and 3, we cut off our endpoint here at 3, and we have a triangle. The base of the triangle is 3. The height of the triangle, this height here, we would find by taking 3 as an x and plugging it into our function. So 3 times 3 gives me 9. So this height here is 9, right? B of 3 would be 9. Therefore, the area of that region for a triangle, we use 1/2 base times height. So 1/2, 3 is the base, 9 is the height. So 1/2 times 3 times 9 is 27 over 2, or 13.5. So the object traveled 13.5 miles in the first 3 hours. Okay, so if you're given the graph of velocity, the area under that curve represents distance traveled. Okay, or it represents the value of that antiderivative of your function. All right, the next part of this question was the region corresponding to the time interval from 3 to 5. So between time, so that same function v of x equals 3x between the time values of 3 and 5. This time our space here underneath that pink line is a trapezoid. So we can decompose the trapezoid into a rectangle and a triangle, right? So we can cut off right here where this side meets my line. So this distance is 2 because it's between 3 and 5. This distance right here would be 9, and we calculate that by plugging 3 into the function, right, to get the height. That's 3 times 3 is 9. Then we have to find the dimensions of our triangle. So our base is the 2. If I plug 5 into my function, 3 times 5 is 15. So this entire distance is 15, but we know that this part of it is 9. So that leaves this part having to be 6. So once we calculated our dimensions of our triangle, or I'm sorry, our trapezoid, by breaking it up into those pieces, we would have that the rectangle has a base of 2 and a height of 9. So the area of the rectangle is 2 times 9, which is 18. The triangle has a base of 2 and a height of 6. So the area of the triangle, 1/2 base times height, 1/2 2 times 6 would equal 6. So if you add those together to get that entire area of that whole space, we would get 24. So therefore, that the object traveled 24 miles between the 3rd hour and the 5th hour. All right, so the last two examples, the area function is an antiderivative of the function that generated the graph. Okay, we want to know, is this always true? Is the formula for the area under the graph of any function the antiderivative of that function? And how do we handle curved graphs for which the area formulas aren't known through geometry? So we're going to investigate those questions using geometry and a procedure that we call Riemann summation, or Riemann sums. All right, so here's the idea. In the following figure, the interval from A to B, so A is the beginning right here. They've called A the same thing as the x1, all the way over here to B. So they've shown that interval on the x-axis, and they've chosen to divide it into 4 equal subintervals. So they've taken the distance across right here and divided it into 4 equal spaces. Right? Meaning that the delta x, the triangle, that's a symbol for delta. So delta x is the width of one of those subintervals. So B minus A is the entire width. And then if I'm dividing it into 4 pieces, that means dividing by 4 gives me how wide one of those little subintervals is. Then the heights of the rectangles shown are the function value. So f of, if I plug in x1 into f, I get the height of this first rectangle. If I plug x2 into f, that comes up here. That's the height of the second rectangle shown. If I plug x3 into f, that gives me this value. That's the height of this third rectangle. And if I plug in x4, I get the height of the last triangle. So they've chosen to use what we call left endpoints of each of those yellow rectangles to determine their height. So the area of the region under the curve is approximately the same, not exactly, right? Oops, sorry. It's not exactly, because there's some space here, and then here I'm a little bit higher, but then here I'm again a little bit lower, right? So it's not perfect, but it's approximately the sum of the areas of those 4 rectangles. So the height of rectangle 1 times the width of rectangle 1. The height of rectangle 2 times the width. The height of rectangle 3 times its width, and the height of rectangle 4 times its width. So they're just doing base times height for each rectangle. So we can denote this sum with what we call summation or sigma notation. So it uses the Greek capital letter sigma, which looks like this. So this symbol means to sum the values. Our index letter we're going to use is I. So from I equals 1 to 4, because we're starting with rectangle number 1, then rectangle number 2, then number 3, then number 4. So we're going to do f of x sub I times delta x, meaning if I start by plugging in a 1, I get f of x1 delta x. Sigma means I sum, so I add, then I plug in a 2 and I get f of x2 delta x. Then I plug in a 3 and I get f of x3 delta x, and then I plug in a 4 and get f of x4 delta x. And I stop at 4 because that's the top number. They're just showing you a different way it's sometimes written. Usually it's written with the I equals 1 and 4 on top and bottom. Sometimes you'll see them over here on the front of the sigma symbol though, but they mean that means the same thing. So you would read this notation as the sum, this is the symbol for sum, of the product of f of xi and delta x from I equals 1 to I equals 4. So to recover the original expression, we substitute the numbers 1 through 4 successively in for I, and then write plus signs between it, like I just explained. Okay? All right, so consider the graph of the function 60x minus x squared over the interval from 0 to 600. So we want to approximate the area by dividing the interval into 6 subintervals. And then approximate the area by dividing the interval into 12 subintervals. All right, so our first step is to find our width of each subinterval. So our entire space goes 0 to 600. So we're going to divide that space into intervals, or 6 intervals of the same size. So our delta x, we always find delta x first. 600 minus 0, so endpoint, the right endpoint minus the left endpoint, divided by the number of intervals, divided by 6. So that's 600 divided by 6, which is 100. With x sub I ranging from x sub 1 being 0, meaning this left endpoint, to x sub 6 would be 500, because remember, if I'm dividing into 6 subintervals all of length 100, that last rectangle would have ended at 600, so that other endpoint would be, if it's a subinterval of width 100, it would be 100 units in front of that, which would be at 500. So here's the picture. So you could graph this on your graphing calculator. You'll have to adjust the scale though, because notice this shows from 0 to a max of 600 for the x min and max. And then notice that the y values get really high. They go up here to 90,000. So you would have to adjust your window settings to actually see that on your calculator. But if you change your window settings and then graph that function, it would look like this. So between 0 and 600, if I divide it up into 6 pieces, each width being 100, so starting at the 0, move over 100, another 100, another 100, all the way to the end. So they've shown at 0, we're down here, we don't even have a rectangle. At 100, the height is right here. At 200, the height is here. At 300, the height is over here. At 400, we're here, and at 500, we're here. Oops, sorry. Let's go back. Okay, there we are. Okay, so that would be what the picture would look like. All right, so the area under the curve is approximately the sum from I equals 1 to 6, f of x sub I times delta x. Well, we start with the 0, the first left endpoint. So f of 0, our delta x is 100. Plus, remember, delta x is 100, so moving 100 over from 0 means you're at f of 100 plus 100. Move 100 over from here, so you're at f of 200 times your 100. Move 100 over again, means f of 300 times 100, then f of 400 times 100, then f of 500 times a 100. So you got 1, 2, 3, 4, 5, 6 things to add together, meaning that should make sense because you divided your space into 6 subintervals. So this is f of 0 is 0, so 0 times 100. F of 100 is 50,000. That means plugging in 100 into that function we were given. So 50,000 times 100. F of 200 is 80,000 times 100. Then 90,000 times 100, then back to 80,000 times 100, and then 50,000. So we're just plugging these numbers into the function to get those heights and then timesing them by the widths. And then when I add all of those numbers together, we get 35 million. Okay, part B wants you to divide the same interval into pieces, into 12 equal pieces. So 600 minus 100, that's the B minus A, divided by 12 this time. So that means each subinterval has a width of 50, so they're smaller. So here your x sub i's, x sub 1 is still going to start at 0, but x sub 12, because there's 12 of them, is going to be 50 less than this endpoint, so 550. So here they're skinnier and there's more of them. So there's the first one down here at 0, second, third, fourth, 5th, 6th, 7th, 8th, 9th, 10th, 11th, and 12th. There is a benefit in terms of accuracy to increase the number of subintervals you have because that means there's less error involved in your calculation. All right, so this time we're going to have 12 numbers to add together. All right, so we're going to sum from I equals 1 to 12, our f of x sub I delta x. So we start again with 0. This time we're moving over 50 units each time. Our delta x is 50, right, for this problem. So we start off by plugging in a 0 to get a height, and then we plug in 50, then 100, then 150, then 200, then 250, 300, 350, 400, 450, 500, 550, and then we're ready to add them up. So notice here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So evaluating our functions at each of those endpoints. When I plug in 0, when I plug in 50, when I plug in 100, when I plug in 150, when I plug in 200, 250, 300, 350, 400, 450, 500, and 550. These are the results of plugging those numbers into F. And then each of those get multiplied by the 50, and then they get added together, and I get 35,750,000. So this can be time consuming, right? Especially if the number of subintervals is large. Okay, but that's basically this section, okay, doing what we call a Riemann sum. So the area under a curve can often be interpreted as in a meaningful way. The units of area are found by multiplying the units of the input variable by the units of the output. Okay, it's crucial that your units are consistent. Sometimes you can use geometry to find areas if you have straight lines as your graph. So if you have a graph that is linear, you can divide your space into rectangles and triangles and trapezoids and just use geometry. A Riemann sum uses rectangles to approximate, not find exact values, but to approximate area under the curve. And again, the more rectangles you use, the better your approximation is. And then moving on, we're going to talk about this notation, this indefinite integral or antiderivative symbol that we saw before. If we put values on the bottom and top from a to b of f of x dx is how we are going to represent the exact area under the graph of a continuous function. So we'll learn that eventually later on in chapter 4. Okay, so that is the end of section 4.2.